We're now going to derive equation 20.25, which is the emitter output impedance. The first thing we're going to do is we're going to take this basic circuit over here, and we're going to write the AC equivalent model. So to do that, we're going to look from the output into the circuit. So this is an unusual way of looking at the circuit. So we're going to stabilize everything from the output looking towards the input. Now, what the input, of course, sees, what the output sees, is this resistor in parallel with that resistor, in parallel with that resistor. And that's because we short circuit the capacitor, we short circuit the supply, we short circuit this one. These three resistors are all in parallel. So we'll just write them all in parallel. Just call them RTH, R Thevenin, where R Thevenin is equal to RS in parallel with R1 in parallel with R2. Now from there, we go into the transistor itself, and we have RE prime. And coming out of the transistor, we have simply RE. Now, this circuit is a little bit more complicated than what this illustration shows, because we have the collector, which is injecting current into the transistor as well. That collector is located right here. Draw it as a current source. Now, in this part of the circuit, the current which is flowing is IB. In this part of the circuit, it is IC. And in this part of the circuit, it is IE. So we can't write Kirchhoff's voltage law in the standard way by just trying to write the currents around the loops, because what we're trying to do is find the impedance from this perspective, looking into this node. So how are we going to do that? Well, we recognize that base current, IB, is actually equal to IE divided by HFC. Now, what this tells us is that we can actually change this expression, IB, to an equivalent IE. And that is if we divide everything in this side over here by HFC. So we're going to do that. We're going to take a look at what the circuit sees from here, Z out, looking into the circuit. And what we're going to notice right off the bat is that Z out is equal to RE, emitter resistor, and that's going to be in parallel with this, in series with this. So it's in parallel with RE prime, and that's in series with this value, R Thevenin, if it is divided by HFC, thus keeping the currents in this loop IE, and therefore not changing the impedances. So there we have it. The output impedance looking into the emitter of a common emitter amplifier. Now this is a very interesting expression, because notice that when we looked at the input impedance over here, that Zin at the base, that was equal to HFC times RE prime plus RE. So notice that if we're looking into the transistor with the base, the impedances that we see, the RE prime in here and RE over here, get magnified by the beta or the HFC. But if we're looking from the emitter back through RE prime and whatever is on this side, then whatever is on the other side of the collector, all these expressions, gets divided by beta or HFC. Something which is very interesting about this circuit is what happens if this stabilized impedance changes value. For example, if the source impedance goes to 0 because this is an ideal source, then this expression here goes to 0. And that means that Zn would simply be equal to the parallel combination of Re and Re prime. So this would have some impact on the output impedance. This helps us to appreciate that in this circuit, the source output impedance affects the amplifier output impedance. Now, many pieces of test equipment and many fields of electronics have specific output impedance requirements. For example, in radio frequency circuits, Z out is typically 50 ohms. For telephony, it's generally 600 ohms. For cable TV, it's 75 ohms, and so on. So one would have to take into account these input impedances in figuring out exactly how the circuit is going to respond to any specific input.